So question 2, A-level worthy, but probably a little bit more than they would want. We've got 6 different acids here. I've given you the Ka values. Remember, the bigger the Ka, the stronger the acid. And now what I want to do is explain the differences between various pairs. So we'll start off with 1 and 2. Formic acid is methanoic acid. So there it is right there. Chlorocarbonic acid would be this one. Now I've kind of cheated a little bit, which is why there's the star there. Chlorocarbonic acid is not a stable species under most conditions, certainly not in water, but I'm putting it in for us to compare the chemistry. Now then I'm also saying between 3 and 4, 3 is acetic acid right there, and then 4 chloroacetic acid, so we got a chlorine instead of one of the hydrogens. Now what we see between 1 and 2 is replace the hydrogen by a chlorine, and the acid becomes stronger. Between 3 and 4, replace a hydrogen by a chlorine, and the acid becomes stronger. Why is having a chlorine there better than having a hydrogen there? And the answer is, of course, that the chlorine atom is very electronegative. The chlorine atom pulls electrons away. It is said to have a negative inductive effect. And so what it will do is it will stabilize the conjugate base, because, of course, what we're talking about here is when an acid acts as an acid, it donates a proton, so it's got an extra electron. The more you can stabilize that extra electron, the better the acid is going to be, because the happier it's going to be to lose the proton. So the more electronegative atoms you have in there, the better it is. And that's exactly what we're seeing. Replace a hydrogen by a chlorine, we're stabilizing the conjugate base. And you can kind of see why with these pretty little pictures. Here's the conjugate base of carbonic acid. Here's the conjugate base of chlorocarbonic acid. Got the negative charge that initially is just stabilized between the 2 oxygens via resonance, but when you've got the chlorine there, sucks away a little bit, shares a little bit more of that negative charge, making this a happier species than that one. Same idea with the ones based on acetic acid. Again, there's the negative charge being shared between the 2 oxygens by resonance. Got this chlorine here, sucks away a little bit more of that negative charge, stabilizing the conjugate base. Now let's think about 1 and 3. So what we're doing between 1 and 3, well, 1 is formic acid, so methanoic acid. 3 is acetic acid, otherwise ethanoic acid. The difference here is that we're replacing a hydrogen by a methyl group. When we do that, we make the acid weaker. You see, formic acid is 10 to the minus 4, acetic acid 10 to the minus 5. Why is putting this methyl group there worse for the acid than having the hydrogen? And the answer is the opposite to what we saw with the chlorine. CH3 has a positive inductive effect. In other words, it pushes electrons towards this carbon. Now, this carbon's already got extra negative charge. It doesn't want any more electron density. So having this pushing that electron density ever so slightly, but enough, pushing that electron density towards the carbon makes this conjugate base less stable than this one. Thus, the acetic acid is a weaker acid than the formic acid. Now between 2 and 4, so chlorocarbonic and chloroacetic. So here we got the 2 ones with chlorines in, and the chlorocarbonic is stronger than the chloroacetic. Well, there's the 2 of them. There's the chlorocarbonic, there's the chloroacetic. Okay, we already know from part A that chlorine has got a negative inductive effect. It pulls electrons away. So there it is, pulling electrons away. Well, here the chlorine smack on the carbon that is pulling the electrons away from. Here the chlorine is 1 carbon removed from that carbon that needs the electrons moved away from it. So therefore, it's going to be better effect here than there. Okay, the chlorine is closer here than it is there, so it has a bigger effect. Thus, the chlorocarbonic, this one, is a stronger acid than the chloroacetic, this one. Finally, we're comparing 5 and 6. 5 is oxalic acid, and 6 is malonic acid. There's oxalic acid, there's malonic acid. First thing that leaps out at you is we got 2 acid groups. They're dicarboxylic acids, so that's why they have 2 values. First value is for losing the first proton. The second value, which is always much smaller, is for losing the second proton. Now explain the differences between the first values. So here we are. The first values: oxalic acid, this one, 10 to the minus 2. Malonic acid, this one, 10 to the minus 3. Oxalic acid is a stronger acid, therefore, than malonic acid. Why? Well, there's two reasons. First is an inductive effect. Think about adding this extra COOH group in there. You've got two oxygens, two nice electronegative atoms. So therefore a COOH group, like chlorine, has a negative inductive effect. It's sucking electrons to it, thus stabilizing via induction the conjugate base, that extra charge. Now, of course, in oxalic acid, this is right next door to it. In malonic acid, it's one separated. So therefore, 5, you're going to have a bigger inductive effect in oxalic acid than you do malonic acid. But there's also a resonance effect here in the oxalic acid, because you've got here carbon that's already set up to have pi bonds, a carbon that's already set up to have pi bonds. So therefore we think about just say losing this proton here. So we got this extra electrons there. Well, that of course can be shared, as we've seen usually within the same carboxylic acid group. So we've drawn it with a sort of dot, dot, dot with the minus charge in there up till now. But now you can have extra sharing of it, because you've got this carbon here that can enter into that extended delocalized electron system. So there you go. Electrons come from here into there to there. And so we have this nice resonance stabilization, and then that can stabilize even further, continuing on round. So you've got extra resonance stabilization of the conjugate base, okay, which is particularly nice and makes oxalic acid a stronger acid than it would have been anyway.